Everybody, and we're very happy to have with us today Matania Ben Artzi, and he will tell us about splines, discrete biharmonic operator, and approximate eigenvalues. Please.
Thank you for the invitation. I enjoy the talks here. It's a nice seminar. Am I heard well?
Yes.
So this I can put in.
Yes. You should put it on.
Ah, okay. Or in a pocket?
Yes.
And what do I change? Here. So this part, the part that I'll be talking today, is mostly a joint work with my ex-postdoc, Guy Catriel, with my professor.
On the other side?
I like that.
Wait.
Here, okay? Now it's okay?
Wait a minute.
Who is now a professor at Browder College in Carmel. Okay, so I just remind you of the biharmonic. It is sort of underprivileged operator for some reason, the biharmonic operator, but from the early days of writing differential operators, it appeared it was the Buckling plate equation by Euler. It's an elasticity theory, and elasticity theory is actually all built around the biharmonic, but it's mostly done by engineers, physicists. The pure stream function formulation of the Navier-Stokes two-dimensional equations. And so this is again the same as the Buckling plate, and there is a nonlinear term, the flux term, which causes all the problems. Okay, and it is a very nice formulation that Lagrange actually wrote down, because in modern language, it means that we are looking for psi exactly in the elliptic space, which is correct, the H20 with the boundary conditions, which are the no-slip conditions. But we are not. There is those of you who are interested in sort of history, but also fun reading. There is this review paper, which appeared in Applied Mechanics Review by the Ukrainian Meleshko, and selected topics in the history of the two-dimensional biharmonic problem. And it has 758 references, huge work, and it includes all kinds of things, prizes by Napoleon, and competitions, and cheating by Sophie Germain, all kinds of things. But it's very interesting reading. Okay, if you look at the 1D biharmonic operator, the kernel Green's function of the biharmonic, for U that's the domain of the operator, actually the self-adjointness domain in a finite interval. So the solution of this equation, that is the inverse operator, is given by a kernel, of course, kxy, and there is an explicit form for the kernel that you can work out for yourselves and see. It's an exercise and sort of spectral theory of ODEs, simple thing. So, and this will play a role later on this K, but I'll remind you here. Eigenvalues, of course. So, mostly I'll try to navigate so that it's around the topics of this whole semester, spectral theory and so on. So, we concentrate on eigenvalues today. The eigenvalues of this operator are given. You take the scale, the correct scale, which is lambda is equal to mu to the fourth, mu bigger than 0. An eigenfunction is a combination of sine and sine h, cos, so on. And the equation that is the mu's that determine eigenvalues are given by this transcendental equation, cosine mu, cos mu is equal to 1.
This is on an interval, or?
What is that?
Is this on an interval?
On an interval, yes. This is with the conditions, but that's...
What are the... Go on.
Yeah, the conditions, H20. So, explicitly means that the function and its derivative vanish at the endpoints, which is the standard elliptic thing you want. I'll come back to it. So this is a transcendental equation, and this is what later on in this spirit I'll call the say an algorithm for the eigenvalues. So that's an algorithm algorithm in the sense that you solve an algebraic equation, the transcendental equation, you find the mu's, and then you get the eigenvalues. So here the first one is 500 and so on, and so you solve it by a simple, straightforward argument. I didn't mean that. So the operator biharmonic.
By spectral calculus would say it's the square of the Laplace, right? Or is this a different operator then?
It's a different operator. That's the whole trick. In fact, there is a few pages in Davis' book on spectral theory to show why Laplacian squared is not Laplacian squared.
Yes. Okay.
But there is a connection. For example, here you will have an answer to your question. If it has to do with Laplacian squared, and you know the eigenvalue for the one-dimensional case is 500, so you imagine you have some kind of a sum of tensor products or separation of variables or whatever you want. So you expect the eigenvalue here, the first eigenvalue, to be what? Matthias, go and give me a guess. It should be, if it's a sum of tensor products, it should be the sum of the two basic. So it should be something around 1000 and so on. So I'll surprise you. The first eigenvalue here is the same 500, almost the same as for the first eigenvalue on the interval. And so this is the first eigenvalue. And you think it's easy to find, but then there is no algorithm for its computation. So actually, here is a problem, an elementary problem. Try to compute lambda 1 for the biharmonic with the classical elliptic conditions, Lopatinsky, Shapiro, whatever you want to call it. I won't do this now. And try to find the first eigenvalue like we did before. This is why I emphasize in the one-dimensional case, you solve the transcendental equation. And here, there is no algorithm. This first eigenvalue, actually, I took from, there was a whole thesis of someone in Germany that was devoted to finding the first eigenvalue by all kinds of techniques, sort of numerical analytic, but without proof sometimes. So it's a major problem still. And the motivation for what I'm telling you, what I'm still working on.
So how is this known, the 525? This is...
They use all kinds of a mix of methods, of finite elements, and all kinds of things. I'm not familiar with myself because I'm not in this. I want to try another way, so I don't know.
What does known?
Yes. What's the error here?
This statement, okay, I posed it.
This thing, the squiggly lines. What do the squiggly lines mean?
I don't know. It's after this comes something that, yes, I don't know. I can quote that these people are computing it. Of course, you can use Euler's method. You can go to the buckling plate and push it in all directions and see what are the nodes.
But there's something rigorous there, or is it all?
No. Not only that, Matthias, but I posed this question to the ChatGPT. This is what we are doing. Is there an algorithm, or what is the way to compute the first eigenvalue of the biharmonic? You can do it on every form, right? And the answer was, I don't know.
Really?
Yes.
I don't know.
Yes, something like that. Sorry. No, it said something like, there is no such algorithm known. Or something
That's
like
different. I don't know. That's different than I don't know.
that. He is modest. He says, if there is nothing in the literature, I don't know. Okay, so not only that, so here is a challenge. I mean, it is the simplest of all problems. It's on a square. It's Laplacian square. Okay, find it. And we know everything about the theory. I mean, it's not a smooth domain, but it is what Agnon calls the cone property. So it's convex, for example, and so on. So you have the elliptic theory well in place, whatever you need. There are still questions about if I go into that, about the blow up of the gradient at the corner points. What is the rate of blow up? You know, there is a singularity as we know from electrodynamics. Okay, more to it. Boggio and Hadamard conjecture, 1908. Actually, it was declared 1908 because Hadamard gave a talk at the ICM in Rome. I think it was ICM number 4, 1908, and he posed this as a conjecture. Green's kernel for this operator, exactly this operator, in all domains, in any convex domain, is non-negative. This was known as the Hadamard conjecture. Actually, he forgot to mention Boggio, but Boggio, Italian mathematician, proved that it is correct in a disk, for example. That is, the Green's kernel is non-negative in a disk. So this is Boggio. And he raised the question.
Sorry, what is the Green's kernel? What do you mean by the Green's kernel here?
The opposite, the inverse, yes, there is a kernel. By elliptic theory, always you have for the inverse of an elliptic operator, you have the inverse is a kernel. Green's function, they call it kernel. I think, what is that? No. And Boggio did it. It is very complicated, complex thing in terms of all kinds of special functions and everything. No. There is, try it for yourself. That is the mixed term makes it difficult to, even not with r theta coordinates, which it did. So this was the conjecture. And everybody believed it was true, especially the physicists. If it is not true, this means that you produce negative, you have something positive in the right-hand side, and if it is limited to that area of negative behavior, you get something like the stream function is opposite to the vorticity or something which is non-physical. Of course, it's not completely true because there is a nonlinear term. Anyways, everybody believed it was true, and then it proved to be false. Garabedian, 50 years later, almost, he constructed actually an ellipse, a certain ellipse, and then in the ellipse, the solution, the Green's kernel for that ellipse, which was quite elaborate, and proved here's negative business. So this was, even in an ellipse, you cannot do it. It is true in a square, but it is not true in some, then they gave, if you have a very elongated rectangle, you take a rectangle which is very, very narrow on one side and then very long, then finally, if it is long enough, you will have also negative parts of the kernel. Yes, in some sense, you're right. Okay, so there were other examples. After that, what is still open is that there are still no necessary and sufficient conditions in 2 dimensions for a convex thing. What convex domains actually will produce a non-negative kernel? Zero. It is true in a square, it is true in a disk, but it is not true in an ellipse. Okay, so now I switch to more the technical part of the goal is to find actually a discrete analog of the biharmonic operator. That is, with the understanding that everything actually goes through some discrete approximation. You want to compute something, so either you take a finite number of eigenmodes or something like that, but it goes to a discrete thing. And so the effort is first to find the discrete analog of the biharmonic in some kind of a general framework, not just something for that, and certainly not the delta squared square, as we'll discuss. Rest of the talk will be only in 1D, even though I have Petriel, actually, my collaborator went into using all this biharmonic in some models of epidemiology, epidemics, and since the Corona times. So he's busy that, and I'm continuing this thing for the, but there is no final answer. So it will be only in 1D. You approximate, this is a general thing that the general ideology, I hardly have to mention it, but I'll run quickly through that. You approximate L2, say on an interval now, 0, 1 to be specific. So you take, you approximate by finite dimensional spaces of increasing dimension. You approximate differential operator by discrete difference operator. I'll give a few. See? Establish discrete elliptic properties uniform in spaces, and notably coercivity, the relic compactness, and so on. As I said, the general theory, general framework. Okay, so it will ensure all kinds of things that I don't want to go into that. But the elliptic part, the discrete part that I described, the general theory, first appeared in a joint work with Jean-Pierre Croiset in France and Daria Fishelov in Tel Aviv. And Ron Katzir was the time my graduate student a few years ago. Okay, so setup of the discrete operators, as you know. So you take grid functions. So our grid functions will always be on an equally spaced grid. So I'm not trying to go into any other things. The space of grid functions I take as L2H, simply J0 to N. So N is 1 over H. H is 1 over N. L2H has the discrete with scale adapted thing. So, and this is the norm. This is the discrete. And a function fx will lead to a grid function f star, which is our notation. So f star means the discrete part, the point values of f on the grid. That's all. Linear operators will be, and the norms will be as you see. Norm is this, sum up to h. So you have L to H0 will be the one which satisfies also the boundary conditions. And it will be homogeneous boundary conditions for us. And well, you have this, and I hardly have to tell you about this. This appears practically in every talk here, right? So I'm following a tradition in these seminars. The discrete Schrödinger operator, only that here we have to worry about the 1 over h squared. That is unlike the case where you don't worry. It is sort of estimating uniformly, sort of reminds of the semi-classical uniform approaches. You know, when you have an h like that, and you have to do things relative to this small parameter h. And the small parameter h is the basic thing in this game. Okay, so you take truncation. Again, if you want to connect it to functions, to smooth functions, you take a smooth function f, and then you say that's delta x f star. So f star, remember, is the point values of f. So you take this, you compare it to f prime, because this is nothing. And you see that it is an O of h squared. And by O of h squared, I mean that O is always some constant independent of h, depending on f and various derivatives, but not like you see here, but not on h. No, this you get by simple Taylor series. This you get simply, right? You agree? So this is just the standard thing and the standard that you find in every numerical analysis book and the basis of all computations. And what will not work, I sort of tell you in advance, what will not work is trying to make delta squared our candidate for a discrete biharmonic. So this is a no good. No good. That is the delta squared. So
in the sense that it won't converge to the...
It will not converge. It needs boundary conditions that you cannot supply, because then you have a stencil which goes delta squared concentrates, you see, delta squared concentrates around the neighbors. Now, if you apply again the delta squared, each neighbor will bring other neighbors.
Right.
And then when you come to the boundary conditions, you have a problem there, because you have too many points that are involved with the boundary.
Just the three boundary points. I don't know how many
Approximate boundaries. Okay, now you're entering the game, yes. Okay, sure. But this is not the way it's done, actually. And okay, so how to define a fourth order final difference operator? You suggested something. Let's try. And so the cornerstone of our approach of all this elliptic discrete calculus was built on what is called the Hermitian derivative in this classical book of Collatz from 1960 that became classical, and actually you can find the things that are close to the Padé approximation that was mentioned, I think, in Danstow, right? The Padé approximation. So And Collatz is the same Collatz from the conjecture, from the Collatz conjecture, the open, you know the open conjecture? Correct? The 3x1.
Yeah, okay, yeah.
Yes, divide is still an open thing.
Yes.
So this is the same Collatz.
Yes.
And so you define the Simpson operator, sigma x, to be this diagonally dominated three-diagonal matrix. And sigma x is actually considered to be an approximation to identity, because you see the h is considered like a small parameter, and delta x squared is an operator. So this is a perturbation thing, an approximation to the identity, but I mean, formally it's the same operators. And the Hermitian derivative Vx, so game is this, you are given V, and now you are given V in a discrete world. Mostly I shift to the discrete world, I'm not talking about the continuous one. So in the discrete world, you have a V, and you want to differentiate. So the way you differentiate is that you define Vx as sigma x acting on Vx should be equal to delta xv, which means that you have to invert to find Vx, which is the unknown here. You have to invert Cx with sigma x, which is a tridiagonal, diagonally dominated matrix, which is no problem too. So this is the definition of Vx, of the derivative. The motivation comes if you want, if you take W to be a function. So this is just a motivation because I'm not going to use it. Here, sigma x acting on a V, on a discrete vector.
Why?
This is the Simpson. I mean, we teach it in info. This is when you want to approximate integration by matching a parabola. This is what you are getting, the Simpson's rule for integration. So this is why I entered here the Simpson operator. If you want. The deeper thing comes from here, actually, but leave it alone. And so inverting this matrix. And if you take a function W, you see the rationale immediately, because you 2h times the sigma x of W is, as I said, the integral of W prime. This is up to parabolic approximation. And this is exactly equal to the same 2h times the delta xw by definition. So eliminate the 2h and you get exactly the sigma x acting on what should be the derivative is equal to delta xw. Again, but the approximation is a good name.
Sorry, what is W prime star?
W prime star is W prime, the function, which is supposed
to W.
The derivative of W
Yes.
evaluated at grid points. As we said, star means that you discretize that function. You look at it at various grid points J, because here you have only xj plus 1, J going between 1 and 10.
Okay, but this is not an equality. This is an almost.
And this is infi equality. This is the Simpson's rule. But I mean, I meant it as a motivation. So finally you get that if you want to integrate W prime, you get this equation and compare it to this one. And then you forget about this motivation. Okay, so this is the Hermitian derivative. It is fourth order accurate of first order derivatives. That is, the proposition is that, and this is tricky to prove, that the Hermitian derivative of f star is fourth. It's not even included in Collett's book. Accurate. That is, if you take a function which is sufficiently smooth, and you take the maximum f of the differences. So again, this is f prime evaluated at the grid point, and this is f evaluated at the grid point, differentiated a la Hermite derivative.
So this Hermitian derivative, this is not the local operator?
No, it's not a local
It's not
operator.
the local operator.
You have to invert the tridiagonal.
Right.
So the miracle is that you don't do it locally for the derivative, but you do it globally. You are given a global vector and you get a global vector of derivatives, so to speak, for that. And it is O of H to the fourth. It is optimal in some sense. It can be explained. And this is not easy. And this is the corner point. So it means that this is the working tool in some sense. And of course, the first thing you note is that you don't even have the integration by parts formula. Even that is forgetting about boundary terms. And still it is useful. F star is the you first evaluated grid points. And once you evaluated grid points, you take the x by the Hermitian rule. The Hermitian derivative of F star relative to the point evaluation of F prime.
X means Hermitian.
Yes, always. Like, you know. Star is, as I said, it is the point discretization of a function F. Okay. So here is the biharmonic discrete operator. So you take V and Vx, both of them with zero boundary conditions, which are the natural boundary conditions for this operator, the biharmonic, and you define the discrete. This is the most boring and the most unexplained part of this talk. Why should anybody think of taking delta x, the fourth order derivative, instead of any delta squared, or something like that, to take it as a difference morally of two types of second order equations, second order operators, derivatives. Like delta x Vx means that you differentiate. So that's a version, a discrete version of a second order derivative, right? This is, of course, the Schrödinger operator. So these are the difference of two second order derivatives, and it gives you, up to scaling, you have to divide by 1 over h squared, the definition for the discrete biharmonic. One thing here is to convince you, and gradually you will see how interesting this formula is and how natural in some sense, but it takes time. So only natural boundary conditions, again, the discussion with Jonathan, I mean, what we need is only the boundary values of V and Vx at the edges. We don't have to invent like near boundary points, ghost points, and all these things that numerical analysts actually do.
Vx is this is not explicit in V. Vx you obtained by applying this inverse of this tridiagonal matrix.
Exactly.
V.
Yes. Yes.
This is a mysterious.
Yes, yes. Because it is some kind of a derivative of V, and then you apply another derivative of V,
right,
which is more standard. And so you get a second order. Of course, the Vx is non-local, right? And again, you do it relative to this, which is local. And you apply only natural boundary conditions. And this is important for elliptic theory. You always use what you have, actually, and what you need.
No, but what I'm saying that the boundary conditions are not so natural in terms of V. Because Vx is
no, it's you impose. You cannot have Vx without knowing boundary conditions also of Vx. Because otherwise you cannot do the inversion. Let me proceed, but it is V and Vx need to vanish at the boundary for a good reason. Okay, so this was introduced not in this form, but in another form by physicists in 1998. And here our colleague Kraz actually used it in computations for Navier-Stokes for the first time in 2001. That it connects to the formulation that I gave in the first page. That is how you do the biharmonic a la Lagrange for Navier-Stokes. So he did exactly that. Okay, so what I just said, that this discrete biharmonic is constructed as difference of second order discrete derivatives. And it depends, once you have Vx, if I give you Vx and you do it like a preparation work actually in advance of doing calculations. So you do on the side, you do the V to Vx routine, and then you need only J plus minus 1 indices. neighbors, which in the language of discrete people, numerical analysts, it's called compactness. That is, you have a compact thing, something that needs no more than 2 points, even though has to be appreciated. You are talking about the fourth order derivative, and all you have to do is values at 3 points. The two neighbors. Okay, let me fourth order replacement. Here's a claim, truncation. Suppose that, so truncation means, as we said before, we want to see how good we are. I mean, okay, we introduce this delta x4. Px is a regular function with 0, 1, vanishing with its derivative at the endpoints. Then the discrete biharmonic operator, delta x4, has a truncation error, which is an delta x4. So you take again, phi star is the grid evaluated function from phi. So you take this discrete biharmonic. You take the fourth derivative of phi and then evaluate at the grid points. And what you get is this kind of estimate, delta x phi star minus the opposite, that is phi 4, you differentiate 4 times and then apply the grid evaluation, is estimated very explicitly by this. Now, this is tricky. This is not so simple. This is not just Taylor thing. And the notation phi 4 star, again, I repeat, it stands for phi 4 evaluated at all those grids. Okay, so this is the claim of a truncation error, which by itself has to be done. These are technical parts.
That's where it's much worse.
Much worse. Yes, you cannot get this, and you will need to take some kind of approximation at near boundary points, because otherwise you don't get a delta square delta square. Also the interior, yes, definitely. Maybe is there a little space station? You know what? In order to give some motivation of the Hermitian derivative, let me sort of digress for a second and do what do I have? You want another thing, which is all I need is this part. So you take, say, 0, 1, and you take a function, and okay, let me define first the subspace. So this is x1, xj. So you take a function which is, this is the space of functions that are piecewise linear, continuous, and vanish at the endpoints. So this comes from the finite element industry. So this is a subspace, right, of L2, always L2, capital L2. Okay, now take the same grid, and say you have xj plus 1, and now you have values, and you say vj plus 1, etc. And then you take from these values, you take the piecewise constant function, which you call, I don't know, piecewise constant, call it delta x of v, which means that it is piecewise constant and it is vj plus 1 minus vj divided by h in every interval, right? Normally, so this is just sort of the local, what do you call it, a difference function. Okay, so you get such a function, such a step function, okay? For every interval, you get a constant. Okay, now you take the projection of this step function. So this is in L2, of course, capital L2. You project this function into this subspace. Okay, you can always project. You have a function which is not in the subspace because it is not continuous. You project on the subspace, and then you get something, and you get values here. And you know what? The values that you get at the points here are exactly the Hermitian derivative values of the enzyme, which is a nice exercise maybe for functional analysis. It involves only projection, but it's not true. It's something. Okay, so I come back to this. So I wanted to give, I cannot avoid an example just to show you the sort of the power of this. It has nothing to do with the rest of the talk, but you want to solve an equation like that in an interval with the standard conditions, and you take an f to be this function, this innocent function. Actually, to get f, you start with u, of course, and then you do the differential, and you want to recover u from f. I give you f, recover u, right? With this, and do it by using, so you replace everything you want to have a discrete version, provable in terms of convergence. So here is our discrete biharmonic, DBO. Then this is the second order derivative matching this and so on, f star. So you solve this, and this is, you solve on a number of points in a second, and this is what you get if you're using only 7 grid points. So n, capital N is equal to 7. Just concentrate on this part of the thing. That is, you get u, so you are given f, and you want to get u. With the minimum number of points, of nodes, just 7, then you are getting, you actually recover u, you recover also the derivatives, but you recover u remarkably well, and this is true for a lot of other functions. And this, try to use your favorite thing or put it on MATLAB, and you see it's not working for 7 points. So this is just to justify. I don't want to do this. Coercivity, I'll do quickly. So now we are entering into the elliptic world, discrete elliptic world. So proposition about, forget it for now, the bounds. I want to concentrate on the coercivity property so that you have a C bigger than 0, independent of A, so that if you take the discrete L2 scalar product, delta X for ZZ, it dominates without any remainder term, it dominates the L2, little L2 now, norm of Z, the derivative of Z, and the second order derivative of Z, which of course is exactly what you expect. This is the form, if you go, this is the bilinear form for the elliptic operator, biharmonic elliptic operator, for any grad function like that. So this is called coercivity. And in elliptic theory, this is exactly the sharp Gordon inequality. Now the trick here, so as we said, okay, you prefer to use delta squared, and you insist. But try to see if you can have this. The trick here is that you need to have such an estimate for all H. So not only that you have one for the sharp Gordon inequality, that you have one function which dominates, you know, so with this is the elliptic analog of this is of course the domain of the bilinear form. So that is the domain of the square root of the formal self-adjoint operator in elliptic theory. But you need to do the fact that it is for all H with the same C, which is tricky, which is normal. Okay, so we have this coercivity property that I want to mention. And then, thanks to coercivity property, you have, you can actually define, because it is positive, say, you can define this. This is exactly the analog of the bilinear form on the classical elliptic theory. And the scalar product is symmetric positive. This scalar product here that you define by this is, again, symmetric positive, definite, and on such functions, satisfying this condition. proposition. If you have, let F be in C2, so I want to connect, say, to the continuous forms. So F is C2, and you take with the boundary conditions solution to this. So if F is C2, then it is H6. Let V be the solution to this, so the discrete solution. So what I'm claiming is that the discrete solution, so this is the convergence part. It actually converges, so the solution to the problem, to the discrete problem here, relative to the continuous problem here, you can estimate by degree of H to the 3/2 times a very explicit notation. And the convergence, actually, it says that also here included are derivatives, so it is better than the usual elliptic theory. And so, you know what, I was planning to show you how close it is to elliptic theory. So we want to have this estimate for U star minus V. And actually, and you see in particular, if you take V is the inverse of F star. So you take the inverse of F star relative to U star, and it satisfies this inequality as part of the general. Yes, please.
Sorry, why not being H6?
No, it turns out to be, I wrote it because otherwise you would ask, if F is in C2, so it's in H2, and then by elliptic theory, this forces you to be H6. And I need F in C2 in order to have these derivatives. So the H6 is a result. Okay. So here is a proof. So I want to prove this thing, and you'll see that it is, if you prefer the terminology of Lax-Milgrom theorem, it's the same thing. So you want to estimate U star minus V in this norm. And so it is this, the supernorm by definition, Z when Z satisfies, when Z is a unit vector, right? Supernorm is. So this U star minus V acting on Z is delta X for of U star. So this is by definition. By definition, to go from here, the definition of this scalar product means that you apply the delta X to the 4 and then use the usual discrete L2. So this is just the definition. But, so this delta X for U star minus F star, because delta X for acting on V is by definition an F star. That's how V is produced. And this is delta X for U star minus U4 star, because F is U4 star. So, but now you have the truncation. This is exactly in the Lax-Milgrom. This means that you estimate you have something in the right-hand side, which is not the truncation, but something in the right-hand side, and then you apply the inverse. This is why you need the coercivity. The Lax-Milgrom, if you prefer this, says that BUU should be bigger than a U squared, not only estimated by boundedness. Okay, so this is estimated by CH to the power 3/2 F star, F double star, double prime, F prime, times Z. Because just the Cauchy-Schwarz. And then, so this is estimated by this, and ZH is dominated by this, and this is unit vector in the other scalar problem. So you're done. So this is your estimate. So this is the estimate that you're getting with an H to the 3/2, which is exactly an imitation of the elliptic estimates. Much better. The surprising thing is that, so we had H 3/2, and actually, by some kind of scaling arguments, you show that optimal means this business that it's H to the 4. So actually, what we estimated before by H to the 3/2 is actually H to the 4. But this is not easy, because this needs special properties of various things to come. Okay, now, I'll apologize. I left this PDF in a way that you can consult it, and it is in a methodological way. That is methodologies that I now explain all kinds of things that happen. But I promised you, so including, but I promised you that I'll come to eigenvalues, right? So just do this and summarize results from before. And then if we have time, I don't know how this will go, we can go back and fill in the gaps. You'll see. So I didn't want to change the order. So we go back to the kernel. The idea is now finally to go to eigenvalues. So we go back to the kernel of this. If U is in this, these are the boundary conditions. This is the first page that appeared, the same K here. Okay. So let's say, so the idea is to go to H minus 2, but let me, and omega means that it's 0, 1, but it is, I copied it, it's from a general domain, more than one dimensional. But let me go to the kernel of the inverse of the discrete biharmonic. Forget about this because this needs the spline thing and call it, just look at the corollary. You have a kernel H, so this is the first time that we meet again the reality. You take the kernel KH of this, so the kernel is a certain matrix, right? Is a kernel of a discrete operator, delta X. Go to the -1 that we know from before. By the way, even boundedness, when I say that this is bounded, it has to have the same bound for all scales of H. Which is true when it satisfies theoretic compactness theorem and so on. So the kernel is given no more, no less, but by up to scale H, of course, that I always keep, by the point values of the kernel of the continuous operator that was before. The same kxy, which is a quasi-separable function, which means it's polynomial, cubic polynomial in X and Y, and so on, right?
Not necessarily. Negative.
What is that?
Said that it's not necessarily non-negative.
Not necessarily.
Non-negative. Because of 2 dimensions.
Yes, in 2 dimensions. In 1 dimension, I skipped a proof to show that it must be always positive in a variety of cases in 1 dimension. I have discretization, but there are gaps. Otherwise, I would stand here and declare that I know how to solve the first eigenvalue and they don't. But so this is the K. You see, it is as expected in the general theory. It's a cubic polynomial in X and Y and so on. And so this is what you expect. And as I said, just the corollary, so ignore the rest. The kernel K is just this. Now, this is in some sense remarkable because it means that the delta X4, which was so boring in the beginning, and it raised protests and suggestions for delta square, and so on. So all of a sudden, it is the most natural thing in the world. That is, if you want to define an operator, elliptic operator, through its resolvent, which is possible, it's a one-to-one. So I could say, okay, you know what is delta X4? I'll define its resolvent as an operator, and the resolvent will be this. I'll just up to scale, take H, of course, and take the grid point values of K. And then this is my operator. Only that it doesn't lead to an algorithm, because an algorithm, okay, well, this came much later. For this, you have a journey. You have to go, as I said, I reserve this part. We can go through spline functions and all kinds of other things, but this is not immediate and not.
It's really a miracle.
This is in some sense a miracle. Yes, in some sense, yes. This was not part of the elliptic calculus before, and we discovered it with Guy Catriel through all kinds of things. But this is, given the definition, I was trying to make it more emphasized how boring is the definition in the beginning of this delta X4, and then it suddenly looks like so nice. Okay, so, and it contributes. So this is the kernel. Again, I give you that I could not. Okay, approximate eigenvalues. So we come, I have the 10 minutes to treat, right? And then take a break. Yes, is this true?
So we have free.
So I have 10 minutes.
Yeah, well, it depends if you want to give them time for questions.
One have questions from Zoom then.
Okay. So let me run quickly through that, okay? Because I was planning on roughly an hour lessons. So you take the eigenvalues, lambda 1, and you take a discrete sequence of eigenvalues, so delta x4, so you have lambda h1, lambda h2, etc. And your goal is to show that, say, lambda h1 converges as h goes to 0 to lambda 1, lambda h2 converges to lambda 2, etc. So this is what we are doing in this final stage for this time, for this part. So you begin by taking the trace, of course. So you have the trace of the operator itself, and you have the trace of the discrete operator. And then my proposition is that there exists a constant C independent of H, so that the difference of traces is estimated. Again, when I say H4, always I say optimal. There is some justification to that point.
So in this case, the trace on the infinite trace, this is finite?
Yeah, because the lambda i's behave like fourth order. Yes, but yes. And so, okay, so let me run quickly. So proposition. So, oh. Okay. I remember what I did. Instead, I collected facts that we will need in the proof. So I called them tools because some of them were not proven, the part that was doubted. So first we said that this is OH4. Remember, this was the tool of optimal convergence of the inverse. And the tools number 2 was the kernel is this one. So we have this. Now the proof of the traces. So the traces means that for gamma, I take the diagonal integral, and for this, I take the sum. The diagonal integral, I can luckily compute because it's just a cubic. And cubic times k. And gamma, I can compute explicitly. And then for gamma h, I can also, because these are the values of the k, actually. This is the miracle that happens. So I know exactly how to do the trace of the approximate eigenvalues. And I get this. And so here is your answer. This is the end of the proposition explicitly. Nothing more to it. Question, is it true? So even with the scales, is it true that for every k, this goes to that, as I said before? In general, we all know, of course, the spectra of converging operators normally do not converge to the spectra of the limiting operator. You know that. As I showed you a picture of the first 64 eigenvalues, which means that I take n to be 64, right? The number of grid points is the number of maximum. So you see how they match nicely. I don't want to talk about the case of the square, which is not. And so, for example, if you look at the first eigenvalue, and the true eigenvalue is, as I said, this is the 1D case. I'm not doing anything here too. So if you take 10 grid points, you get something. You see that you quite easily get with a minimal number of points relative for this kind of problem. You get here for 20 points already, you get 2 digits squared. And so these are just calculations, and the true eigenvalue is known from general thing. Okay. So yes.
Is it clear that it should increase with n, or it seems that it increases with n?
That's a remarkable question. No, it is not, and we don't know how to prove it. And it has some implications to all kinds of things. If we knew how to prove that this increases, so here is another open problem.
Not true for the other argument. Or
It-
not true, the other eigenvalues don't increase. So the second eigenvalue, they
This-
don't increase.
It increases here.
Increase with n. Oh, sorry. yes.
Increases here along
Yeah.
along the column. Normally it does. But we ask explicitly for the first one, because the first one will have implications for the first one in the case of the square. Okay. So the second proposition, I'll rush a little bit. So the second proposition is fix I. So you take a lambda I, a fixed lambda I, and you take the distance now, lambda I inverse, so I is fixed, to the whole collection of inverses of the approximate eigenvalues. And I claim that this is also has an optimal, so this is lambda H inverse, and it has also an optimal thing. So how to put, Rami, question?
Well,
Oh, So we want this. But instead, what we are getting is that lambda I minus the distance from the whole bunch. Our strategy for this is that you show that you show that this forces, the distance is attained when I is equal to I here. That is that we have the lambda HI. That is that all the distances, you see, that if you take a distance from an approximate one of the members of lambda H inverse, which is not I, then you get bigger than a constant. And then this finishes. I'm telling you that here you have a distance to a subset. I'm telling you that this subset, n minus 1 of its terms are far away. So it leaves only one, right? So to prove this, you go, okay, I'll do that. So you take this, you look at some individual, the eigenfunction corresponding to lambda I. So you can express it like that. You have again the kernel. So once you have the kernel, and you fourth order accuracy means that, so you have the kernel acting on phi giving you lambda I minus 1 of phi. Same function, this is a function. So you get this optimal thing that we discover, which can be written in the way that lambda I inverse minus delta X inverse as an operator acting on phi star. Phi star is the full discrete value of the eigenfunction phi is H4. Now imagine, to simplify, imagine that this is phi is 1. It is not 1 in terms of the norm because you are taking the star, the grid points, but forget about it. Phi star is 1. If phi star is 1, this means that so if phi star is 1, this means that the resolvent is bigger than, see, it's a small difference. So phi is almost a candidate for the eigenfunction, discrete eigenfunction. So this means that this is small. So the resolvent is big. But if the resolvent is big, then you have an L self-adjoint. Remember this classical claim that here is the distance to the spectrum. And so this means that you take the inverse of this. And so you get that this is exactly what you need, H to the 4, in terms of the distance to the whole set. Okay, now tool number 3 is that should stop. You'll see if there are questions. If not, I have just two.
I mean, the people on Zoom, some of them, I don't know if they exist.
Yeah. Because I have two more.
They're really there, right? I don't know.
So I can stop for a quick.
Yeah. So if on non-local participants, do you have any questions at this point?
Shake of my head.
Shake of the head.
None much fun.
Everything was
no
clear.
questions in Potsdam. Yeah.
Yes,
Okay.
very good. So I can continue. Everything was clear up to now. So now
They will leave in 2 minutes. Right?
yes.
We don't know about, they're allowed to be.
They're allowed to work.
Yes, they are disciplined.
Yes.
Okay, so now I take sort of a tool. I replace the kernel kxy by a piecewise constant kernel. That is, before we had the kernel of the discrete was point evaluations, grid evaluations. Now I'm not talking about grid evaluations, but some kind of expansion of that. That is, for every grid point, I take a full square around it, and then kh, you see the full square is here, and I take kh to be the k in the middle, that point. So this makes it a piecewise constant kernel, so to speak. So now why do I need it? I want to be on the same footing. That is, so that I work in sort of L2 for the same spaces. So you take this to be LH minus 1, which is the KH kernel, the operator with kernel KH. It is compact, positive definite, and so on. And then there is a claim that you can verify that the set of eigenvalues of this LH inverse is the finite set lambda H inverse. it is just a simple exercise through definitions. Here is a theorem from spectral theory, which has an interesting history by itself. It was first discovered by Marcus, 1964, and then Cato rediscovered it and had a correspondence about it. And he didn't know about the work of Marcus. And they produced basically similar results, which means you take now nothing to do functional analysis, and take K and K tilde, two compact self-adjoint operators on the Hilbert space with eigenvalues like that. Suppose that it's always positive, which is not part of it. And then the sum of mu K minus mu K tilde squared is actually estimated by the, without any constant, by the Hilbert-Schmidt norm of the difference. Remind you, the Hilbert-Schmidt is just this. And so this is the tool we needed at some point, because then from spectral theory, our application to the problem is we needed to modify Cato's proof, because Cato's proof and statement included all kinds of similar values otherwise and so on. But so we produced another simpler, in the article, another simpler proof. But the result, the final result is that if you look at this, and by the way, all this is true, I should say that most of this presentation actually is valid in, say, at least 2D as well, most of it, except for the points that I really need. Okay, so it remains in some sense, mostly the connection, this magic connection between the kernel and some kind of an algorithm. That is, I can formulate this whole thing, get these eigenvalues, but I'll never know how to get an algorithm for the language. That's it. Anyways, so the sum of the squares here, of the inverses, is estimated by this, which means that lambda hj minus 1 minus lambda j minus 1 is ch, which is a very bad result. I mean, if you do individually, right? I do individually, just forget about the sums and take individually. So I get something like this, but this is bad. But it's not so bad. This is the first step, like a bootstrap thing. You know that this is close, and all you know close to the degree that you have some h in there. And so all you need is then to show that the others are not so close. And then you go back to the result about the distance to the whole group as h4. And you say the only candidate is this one, so this is just an initial estimate to be improved. Yes.
Okay, but in the previous slide, so lambda hk inverse, where k is too large, is zero, you take to be zero.
No, I take
in order to apply the Hilbert-Schmidt. Yeah.
for this. Yes,
Yeah,
I'm.
for the second term, it seems that
No, this is lambda k. This is the whole the original operator, which is an infinite series of.
you didn't take the difference, but you take the difference between two operators.
Yes, and
the
I take this,
term.
and yes, there is something.
You take the lambda hk minus 1 to be 0. No? Or am I...
No, I take only lambda hk when I'm allowed to do that, up to n minus 1.
So when you're not allowed to do it, you can still...
It's not in the inequality. And you're right that behind it there is a story going from the infinite to finite. This is what I alluded to. But yes.
Whether there is some
No, I don't know of any intuition, but it's true that here I'm using only the first n minus 1 eigenvalues or n eigenvalues, and here I'm using all of them. And so in order to conform with the theorem. And then yes, there was an issue behind that they are not on the same footing, but let me forget about it. That's a valid question, yes. Okay. Now I'm claiming that finally it's CH4. That is what we need, the optimal convergence of the eigenvalues. So the proof is, so you combine two results. The first is that the minimum, that is the distance, lambda hi from lambda k, the minimum, here it take k to be fixed, you fix k. And so the difference here is estimated. This is the distance of ensembles, as we said, distance from the spectrum. And so it's a distance of lambda k inverse from the spectrum of the discrete kernel. And the second is this one. So we get for any j different from K, this is what I said. You know, all you need is a very modest thing combining these two. You just need to show that for J, different from K, you don't have any chance, in particular, not a chance of this even. And then you are done because you can go back to this. And this is done. This is a simple inequality. You write this J different from K, as I wrote it again here. You take it to be, okay, it is a simple thing. It's, you can figure it out. You take the minimum value of this, and here, of course, they all converge to 0. So the minimum is actually obtained because it goes to 0. And then you get that lambda hk minus lambda k is ch to the fourth, as you wanted to get. And the program is to study the discrete biharmonic operator in the square. Various aspects of that. If you are ambitious, you can take any convex domain. But maybe this is the first step to do. But this in the square, the first eigenvalue, as I said, I want to emphasize there is no algorithm to compute it. Still.
This doesn't give you an algorithm in the...
No, it will give me an algorithm if I could connect the discrete kernel which exists, and I have to work for it. For the discrete kernel, because it is the sum of tensors, and then there is a mixed term, and I have to dominate it. All this is done. But okay, so I get eigenvalues lambda hk, and they're useless in some sense, because I cannot do anything with them. They are not the original eigenvalues that I want. And so, okay, this is a technical detail, which is always the case. You know, how to connect, what is the magic of connecting the kernel to some continuous kernel, which is guaranteed by general elliptic field. Okay, thank you.
Are there any questions other than the ones we've already heard?
Yes.
Yes, I have several questions. The first one, so what is the moral quality of the B harmonic compared to Laplacian square?
I'll tell you this, Laplacian squared will give you what is called the simple plate model, which means that that's technically easy to understand. You take Laplacian squared as you wanted, and of u, and so this is Laplacian of Laplacian u. Now, for you, on the boundary, you have 0 for this. This is what you need for the Laplacian. But now you want to activate the second Laplacian. This is a classical, I think even in Davis' book, it appears as an example of showing how the different norms of the h to the 1/2. Now, what do you need here for the Laplacian? You need Laplacian u on the boundary to be equal to 0, because you act on Laplacian on a function. So this is called the simple plate, I think. If us will see, how is it called? When you and also, and these conditions, so if you put these two conditions together, they have a name. These are called the Navier, because Navier did them first, Navier boundary conditions. But they are not Lopatinsky-Shapiro, they are not, but they can, you have an elliptic theory for them, which is not part of the standard Algorand-Lewis-Neal. It's not, because
So I understand it's different boundary conditions.
not
right?
only different, but not in the framework of elliptic theory standard. You open the book of Algorand, you don't find it there, and Jans von Jenners, you don't find it. But it is true that engineers worked on that, but this does not represent the thing that we want. I mean, you want Laplacian squared with the proper elliptic conditions. So it is true that if you do this, you have all kinds of advantages, because you can do separation of variables and all kinds of things. And then you can use, if I want to add, you know, you have a beautiful theorem to say that, okay, you take, say, in the square, so 2D. So you want to show what are the various biharmonic functions. So you discover that, of course, if P is any harmonic, suppose Phi and Psi are harmonic. Now, every harmonic function is of course, biharmonic function, right? So you take Phi plus X Psi, for example, it is biharmonic. It is not harmonic because of the x, but it is biharmonic. Laplacian square to this, just to differentiate, we say it's 0. Also phi plus, and similarly for y, everything is 0. And phi plus x squared, I think, plus y squared, psi, is also biharmonic, and you have a list of 7 of them. And then the question is, and it was ingenious thing of this was a theorem, but I don't remember the details, that these 7 produce all the biharmonic functions in the square. And then you combine this with the Navier conditions, and then you get something about the biharmonic.
Okay, this is also 2 different physical models, what you.
Yes,
That's.
like always. That is, this is a non-standard with the Laplacian mu, which means not only that it is non-standard, it is not true for flow problems, for example, because flow problems, so if u is the stream function, then Laplacian mu is vorticity. And to say that vorticity, Laplacian mu is vorticity, Laplacian of the stream function is vorticity. And to say that vorticity is 0 on the boundary, this is good for a whole Japanese school that make out a living of that and, lowering spaces and proving existence, but it's useless. The whole problem of flow is that you have vorticity on the boundary. I mean, we can have a separate talk about that. This is this.
But could you explain to your grandmother what's the difference what you do to the plates in the.
Well, I wish maybe Ras could. This is the clamped plate means that what I was discussing, the elliptic theory, luckily for us mathematicians, goes with the clamped plate, which means that you take a plate and you hold the 0, so there is no movement. That is the location and the movement are 0, that is, at level 0. So this is called a clamped plate, because clamped.
Mm-hmm.
And the other, I think the name is simple plate. Would you remember, Marsha? Simple plate. Clamped plate is for sure. So what we did is clamped plate. What people want to do is eigenvalue clamp.
Geometrically?
Geometrically for what? For the statement how the biharmonic
plate. What is the simple?
I don't want, I'm not talking that I don't know what it means that in the stream function industry, in Navier-Stokes, it makes no sense. In fact, it's misleading because you apply a boundary condition which is bad. The whole action of flow is created by the boundary layers, they say, by the formation of vorticity on the boundaries, which has an elliptic analog, which is called the single layer, by Agmon, I think, single layer, double layer potentials. That is, if you want to solve, you have to add single layer potential. If you want to go to the boundary of a domain and have the integral equation on the boundary. But it's interesting that these are 2 different things. And the Laplacian of Laplacian is easy, in some sense.
Anybody else? More questions?